Yeah, thank you so very much for the very nice introduction. Thanks so much for the invitation. It's really a great pleasure to be here at this amazing event. Now, I think we all know how tremendously successful AI is these days in sciences, in public life, and also in industries. But we talk mainly about software. We don't talk that much about AI computing in the sense of which type of hardware do we compute on. And I would like to convince you in this talk that if you want to carry AI into the future, in particular in a sustainable manner, then we need to rethink the way we do AI computing. Now, we are right now at the beginning of the fourth industrial revolution through AI. We see our lives changing around us on a daily basis. Think of self-driving cars, robotics, telecommunication, also very sensitive areas like the whole legal system and also the job market. And there's not one area in the sciences which is not yet affected by artificial intelligence. And if we look into the future, during the next, let's say, 5 years, we are expecting a radical change of our society in its full breadth. So which role does computing play in this regime? Everybody talks about digital transformation. So this certainly requires ubiquitous computing. Then, generative AI. We heard a beautiful talk by my colleague Björn Ommer from LMU this morning. And this certainly requires massive, large-scale computing and relies on it. Then we have virtual reality, the metaverse. This requires extremely fast computing and also relies on it. And then, last but not least, ICT, which is one core of the critical infrastructure of every country worldwide, completely relies on digital computation. And so in that sense, I think it's fair to say that computing is the heart of modern technology. It powers innovation, transforms industry, and it will change and shape the future of our society. And if you realize how important computing is, then we also realize that we have diverse problems currently with the hardware we compute on. So let's look at a couple of examples in the area, in particular, of AI. I think we all know about the sustainability, the energy problem. And so I brought here for you a figure from the decadal plan of the Semiconductor Research Corporation for the Biden administration in 2021. What you see here is the world energy production, this white line. And now I will plot the energy which is just needed for communication if we use CPUs. That's it. Yeah, and this is actually really bad. We cannot use more energy for communication than the world energy production. If we use GPUs, it becomes a little bit better, but still remember, this is just the energy we need for communication. And because of this situation, we then see effects like this. So a company is building a new AI center, and it's planning the 3 nuclear power plants which provide the correct amount of energy right next to it. So we have a serious energy problem here. Also, another problem is reliability. We see it in the news all the time. AI is not at the level where we expect it to be, in particular also concerning self-driving cars. If you look at this figure here, the stop sign, everybody of you would recognize this as a stop sign, but if you put stickers on it in a particular fashion, the self-driving car might make a radically wrong decision. So also here we have a serious problem, and it's not just a software problem, also a hardware problem. And this is connected also to what's called the computability problem. So there's, let's say, a profound understanding of hardware, for instance, digital hardware, which enables us to analyze on that type of hardware whether we can make predictions, for instance, about the performance. And scientists also worldwide, now there are several results which show that with digital hardware, we have problems with this computability. And related to this, people just talked about the EU AI Act. In a couple of months, every AI software has to comply with the EU AI Act. Also there are many results now which show that with digital hardware, there are certain problems which we will face. And so, you see, with current hardware, we face a lot of problems, so what do we do? And I would now like to delve a little bit deeper into the computability problem and then the energy problem. So, as said, computability, there are many results worldwide. We also work in this direction. We showed, for instance, that the solution for certain problem settings is not computable on digital hardware, for instance, by a neural network. This looks bad, but we also have positive results. Because if you go into the analog domain, things suddenly become computable. And actually, everybody of you know the difference between this digital hardware and analog hardware. Because think about it. If your computer has a problem, sometimes the only way you can fix it is to turn it off and restart it. Huh? Everybody knows. But your human brain, your analog computer, you will never restart. Yeah, I mean, if you have a problem, it kind of wriggles its way and then it fixes itself. So analog hardware is much more flexible. And so this points in an interesting direction, that we need to embrace analog computing and maybe augment digital computing by it in a particular manner. And there are interesting developments, neuromorphic computing. Major companies like Spin Cloud, IBM invest massive amount of money right now to develop neuromorphic chips. Then there's this very new biocomputing and also quantum computing, I think, which we all know. And here in Munich, we also have the Munich Quantum Valley. And so I hope, to a certain extent, I convinced you that we need to rethink the way we do AI computing. If you're not convinced, let me show you another slide. Now we come to the energy problem, and I already showed you this figure. So let's look at what happens if we use novel hardware. Now things become a little better. But then, I mean, if we now also embrace, let's say, theory, and we build a mathematical underpinning like we did on the previous slide with computability, we can do a much better job. And there are beautiful results by my colleague Holger Broche from TUM, who introduced in communication this post-channel theory, and suddenly, I mean, things look much better. And so the main message here is that, I mean, if we are rooted in theory, if we take also a foundational viewpoint, we have the chance to carry AI computing in the future and then also tackle many of those problems. And that's exactly the heart of a large-scale project which we start recently, which is the project Next Generation AI Computing. The key goals are to develop novel, energy-efficient hard software combinations, also embracing analog computing, which is theory-driven, to do it reliably, and also in compliance with legal requirements, and then apply it to communication, medicine, and robotics. Yeah, and so these are some of the core areas of the critical infrastructure of every country worldwide. This is set up between Bavaria and Saxony, and we are very fortunate to get generous funding from both state ministries for science. On the Bavarian side, I'm joined by Holger Broche, and on the Saxony side, we also have two amazing colleagues being involved. Now you might wonder, these legal requirements, I mean, they are so vague. If we now take a theoretical viewpoint, how do we actually do that? And we are very lucky that we just recently started another project which complements this ideally and supports this, and which might also be interesting for if you have a company. So it's a project supported by the State Ministry for Digitalization, here also in Bavaria. And the idea is to formalize the legal formulations of the EU AI Act to then allow completely automatic verification. So if you have a company and we are done with this project, I mean, we have a machine, you put it in, and then you can analyze immediately whether you satisfy the EU AI Act. This is set up between the LMU and TUM, and we are joined by the first AI university of Europe, the UTN, and our colleague Wolfram Burkhardt. Okay, so let's get back to GAIN. Why do we actually set it up between Bavaria and Saxony? That's because we have amazing conditions here. Yeah, so in Bavaria, the state minister already told you about the high-tech agenda, which puts already billions of euros into AI and to quantum computing. And Saxony, most of you might know, this is the microelectronic hub of Europe. And in addition, we have a lot of projects here already in place. We have a 70 million 6G Live project to develop the next generation of communication and a satellite connection already between actually Munich and Dresden, and then several other projects. Two of the AI federal competence centers are here in Bavaria and Saxony, the MCML in Bavaria and SCATS AI in Saxony, and two of the three Konrad Zuse schools of excellence in AI are also here, the RELI in Munich and SECA in Saxony. You see, I mean, we have an amazing environment here, and so this enables us to hopefully soon realize our vision for this project, which is to develop a comprehensive theory-driven framework for next-generation green AI systems in such a way that if you have a certain application, we can tell you immediately how to optimally combine hardware combinations, analog, digital, also combine it with software to get maximal energy efficiency and also trustworthiness. And then when we have that in place, we can go into the applications. They already said one application are communication systems to get provably reliable AI-based communication systems. And also the Federal Agency for Networks is waiting for that because they don't use right now AI for communication. Low-cost, trustworthy medical AI devices also for employment in third world countries. And last but not least, next generation robotics with then reliable robot brains and so the energy efficiency, lifelong learning capabilities. And with this, I'd like to conclude and thank you very much for your attention.